George, you have pieces, right?
Oh, I know.
Meeting on.
We different. So they have. People are liars.
Like actually.
What the hell? I think my first she likes to it was like I bought it out when I was and I
Quiz review.
yo, no, I don't.
Anyone else missing the fall semester review? Gosh, no.
Yo, it is.
And Brandon Humphrey.
In Jersey.
Oh, yeah.
Hey,
Well, one's a ticket.
What?
It's the only truth they gotta say yes.
Is that what you did yesterday?
Okay, guys, the quiz review, sorry, the FRQ review. If you guys can turn to page 3.
Austin, all the
Okay, you're gonna need your calculator. This is another rate in, rate out problem. Okay, and then these involve integrals as well. We know that integral is going to basically change the rates, change the units from rate up to the units that we want. So let me read the problem here. The tide removes sand from Sandy Point Beach at a rate modeled by the function R, given by R of t. A pumping station adds sand to the beach at a rate modeled by S of t. Both R of t and S of t have units of cubic yards per hour. Right. And then t is measured in hours between 0 and 6. At time t equals 0, the beach contains 2,500 cubic yards of sand. So just to kind of spell out what's happening here. So we have this amount of sand that is that begins on the beach. And then we have S of t, which is a pumping station that is adding sand to the beach. Well, the rate at which sand is being added, but then the tide is also removing sand from the beach at a different rate. So we have 3 things that we're kind of keeping track of as we move through our problem. So part A, how much sand will the tide remove from the beach during the 6-hour period? So we know that if we're talking about removal, we're dealing with R of t, but R of t is in terms of cubic yards per hour. We want the amount of sand, which is cubic yards. So what do you think we need to do to R of t to get that rate up to the accumulation of the amount of sand being removed? Yeah, integral. Yeah, so integral, we're going to basically accumulate that rate over that period of time. And that accumulation is going to allow us to change our units from a rate up to the amount of sand. Okay, so we're going to use our calculator. I'm going to have y1 hold R of t because we don't want to have to retype the same function over and over again. Make sure that you're in radian mode. And even though t is showing in your on paper, you're going to use x in your calculator. And I'm just going to go ahead and type in S of t under y2. I'm not going to need that later. So Okay, so we know we're involving integral. So how much sand is being removed? So over the 6-hour period, so the integral from 0 to 6 of R of t through t. Okay, so we just round to 3 decimal places. You can either make it 0.815 or 0.816. All right, part B, write an expression for y of t, which is the total amount of cubic yards of sand on the beach at any time t. So there's this formula that we use for these kind of rate in, rate out problems. And basically, this is kind of keeping track of the 3 things that are involved is, how much sand, because if we're talking about how much sand there's on the beach, it's dependent on or involving 3 sets of information, right? How much there is to begin with, how much has been added, and then subtracting how much has been removed. So this is a formula that we can use in some form or another across different problems. So let me write out the formula that we're going to use. So the total amount of anything at any moment at whatever we're asking for usually is going to be involving these 3 sets of information. So how much is there to begin with? Okay. How much has been added? And then minus how much has been removed. If we keep track of those 3 things, we're going to know how much of that, how much quantity there is at any moment in time. So for us, this problem, y of t, which is the amount of cubic yards of sand at any moment in time, is dependent on, first off, how much there is to begin with. And we know there's 2,500 cubic yards of sand to begin with, plus the amount added. So the amount added, we know it's going to be involving the integral of s of t. So we're going to say the integral, but we're going to plug in t once we figure out how much, how much time has passed. Is it going to be the first 4 hours? Is it going to be the first 3 hours? Is it the first 2 hours? But we're going to be using s of t, but we just want to indicate using a different variable so that you eventually when that t gets plugged in, it gets plugged into a different variable. So that s of x is the same thing as s of t. We're just adjusting that with a different variable so that the t can be plugged into x. But eventually it's going to be in terms of x. And then we're going to subtract out the amount that's been removed involving r of t, which I'm going to call r of x. So this formula will allow us to figure out how much sand there is on the beach, whether it's 4 hours that's passed, or it's 3 hours that's passed, or is it 5 hours that's passed. So part B is just creating this equation that we're going to use in future parts of the problem. Okay. Any questions with that setup? Okay, so this is a very common type of a setup for these rate in, rate out problems. This can show up again in future these integral accumulation problems. Okay, part C. Find the rate at which the total amount of sand on the beach is changing at time t equals 4. So we know that the rate is involving y prime, right? So it says find the rate. So let's find y prime first, and then we can find y prime of 4. So let's build the derivative out of this equation. So y prime, 2,500 would go to what? 0. And then this, we're asking for the derivative of the integral. And what's going to happen here? Yeah, cancel out, second theorem, which means that upper bound gets plugged into the x. And so the derivative of this will just wipe it down to s of t. And the derivative of this will turn into what? Just R of t, yeah. Derivative of integral, they cancel out. Remember second theorem. T gets plugged in for x minus R of t. Okay, so we've created our rate of change of y prime. And then we can just do y prime of 4. Which is simply s of 4 minus R of 4. Now, because S and R, they're already in terms of a rate, we can just plug directly into the calculator, call the function. We don't have to find the derivative of S and R because S and R, they're both involving a rate already. So I have S stored under Y2. I have R stored under Y1. So I'm just going to call, Y2 first, minus Y1. So this tells us that 4 hours in, the rate at which the amount of sand is changing on the beach is decreasing by 1.908. So even though we have the pumping station that is adding sand to the beach, we still have the sand, the tide taking more of the sand away. So negative 1.908 cubic yards. Okay. Yeah, so that negative indicates the beach is losing sand by close to 2 cubic yards per hour at that moment in time, at that 4th hour. Okay, part D. For T value between 0 and 6, at what time is the amount of sand on the beach at a minimum? So anytime we see max and min, we know that they're trying to get us to use which theorem here? It's extreme value theorem. Yeah, so extreme value theorem requires us to keep track of a couple of things. We got to keep track of our critical points and endpoints, right? So we're going to be testing so critical points comes from where the derivative is equal to 0, and endpoints comes from they're stating 0 and 6. Okay, so to find critical points, we're going to set y prime equal to 0. And we have our y prime formula, so we're just going to set 0 s of t minus r of t. And again, we're going to use the calculator for this because we don't, if we try to set s of t equal to r of t, that's going to be a hard equation to solve by hand, trying to figure out what t is once we set these equal to each other. So there's 2 ways to do this, and you guys can choose which way you want to do, but I have a preference. One way is you can graph s of t and r of t. Or you can set them equal to each other. You can graph s of t, graph r of t, and then you can look to see where they intersect. That's fine. But I prefer a different way because if you do it this way, you're going to have to adjust your window. You got to find that intersection, and that intersection may not be easy to find. I mean, it's going to be in the first quadrant, but it could be, it could be having to scale your graph so they can see it. My preference is to do this. Rather graph this and then simply look for the x-intercept. If I do it this way, then I can just scan across my x-axis for when this graph is going to cross the x-axis, rather than searching all over my graph to see where that intersection is. So, I mean, if you choose to do it this way, that's fine. You just have to make sure that you're comfortable adjusting your window and find that intersection. But you can choose either way. I'm going to attempt to do it this way. So I'm going to hold my y1 and y2 in my graph. I don't want to keep typing these functions in. So I'm going to just do s of t minus r of t, which is basically going to be y sub 2 minus y sub 1. And I want to I only want to see this graph. I prefer not to see y1 and y2, even though I want them stored in the function so I can call it. So I'm going to go to the equal sign under y1 and y2. I'm going to hit enter so that it will unhighlight. If I unhighlight it, I'm still able to access the function, but it's not going to show up in my graph. So now I'm going to adjust my window. I know that I'm looking at a t-value between 0 and 6. So I'm just going to adjust my window, x min, x max for 0 and 6. And these values seem manageable. They don't seem really large in terms of the y values. So I'm just going to say -10 to 10. But I can always adjust accordingly if I see it's not showing me a graph that's easy to trace. So I'm looking to see when is that graph going to cross the x-axis. There's my x-intercept. There's my solution. Or there's my critical point that I want to find. So if we do second trace 0, pick a point to the left of the x-intercept, hit enter. And then scroll to a point on the other side of the x-intercept, hit enter again. Get the calculator to find that intersection for you, so 5.117. So we have a potential absolute minimum at t equals 5.117 hours. So now that we have, there's only one critical point and we have two endpoints, and now we're going to plug them all into the y of t equation to figure out, between hour 0, hour 6, and hour 5.1, when is the sand going to be at its minimum? And it's going to have to be one of those three values. So we're going to find y of 0. We're going to find y of 5.117. We're going to find y of 6. Y of 0 is easy because that's just the initial amount. And then the amount of sand at hour 5 and hour 6, we can just plug into our calculator. So I'll do 2,500 plus math 9 from 0 to 5.117 under S. S is stored under Y2 for me. Oops. Minus math 9 from 0 to 5.117. 1. 2493 or 2492. Sorry. Yeah, 2492.369. Nice thing about doing y of 6 is I can just go back and reuse the exact same entry and just change what? Yeah, just my upper bound, right? I'm using the same formula. I just want to go from 0 to 6 instead of 0 to 5. Okay, so the absolute minimum is between these three candidates. What's our lowest amount of sand? Yeah, 2492. Right, this is the lowest amongst these three options. So the absolute minimum, what is the minimum value? So we're looking for the minimum amount of sand. So that's going to be 2492. And that's why when AP exam, when they ask for absolute minimum, they're asking for the Y value. Because if you're asking for absolute minimum, I mean, you wouldn't say, okay, the absolute minimum is 5 hours, right? That doesn't quite fit the answer to the question. So that's why with EBT, they only care about the Y value. They don't care about the T value. Unless they specify, at what time is this occurring, but usually with EBT, they're asking for that Y value. And it says justify your answer. And with extreme value theorem, the way you justify is you just show that you are testing the appropriate candidates, and then you're making your decision based off of those candidates. Any questions? This is a very popular format for these rate in, rate out problems, where they start you off involving integral, and then they ask you to build a formula, and then extreme value theorem to find absolute max, absolute min using that formula, and also involving derivative. Okay, so this is a very common structure for these rate in, rate out problems. Right, let me do problem 5 with you as well. So this particular, these rate in, rate out problems is not going to show up until the second FRQ quiz after the break. The first FRQ quiz is going to be more along these table of values, which are more familiar, and we'll cover this tomorrow and also Friday. Okay, so we'll have some time to do that. But let me start off with this one here. So page 5. The amount of water in a storage tank in gallons is modeled by a continuous function where T is measured in hours. In this model, rates are given as follows. So the rate at which water enters the tank is F of T. So here's F of T. It is rising. So imagine you're just letting water in at a higher and higher rate over the course of the 7 hours. It's going to peak a little bit after 7, but you're just increasing the rate over the course of that time. Okay, so that's the rate at which water is entering into the tank. And then at the same time, water is being let out of the tank at different rates. So between 0 and 3 hours, water is being let out at a constant rate at 250 gallons per hour over a 3-hour period. But then from 3 to 7 hours, it's going to ramp up all the way to 2,000 gallons per hour. So we have this amount of water being let out, and then this amount of water being let out for the remainder of the 7 hours. It says this is saving us a little bit of time. We don't have to graph and find the intersection. They're telling us that intersection, which will be helpful to us. The first is at 1.617. And the second is at 5.076. So I want us to kind of observe what is happening to the water level, though, over the course of this time period. So let's say between 0 and 1.6, what's happening to the water level if this line is above the curve? Is the rate at which water is entering higher, or is the rate at which water is leaving higher? Leaving. So therefore, what's happening to the water level here? It's decreasing. So I'm going to indicate, going to highlight I'm going to use pink to indicate that the water level is dropping, and that this is going to, that because the rate leaving is higher than rate entering, water level is going to be dropping. Okay, what about between 1.6 and 3? Increasing, right? The curve is now water is coming in at a higher rate than at which it is leaving, at least for a moment. But then from hour 3 to hour 5, what's going to happen? Back to decreasing again, because now we have a higher rate at which water is leaving than the rate at which water is entering. But then after 5 hours, back to rising. Okay, so I just want us to kind of visualize what's happening to the water inside the tank. It's going to decrease, and it's going to increase, decrease, and increase. So I just want to kind of have you guys visualize that. Okay, part A. How much water has entered into the tank over that 7-hour period? So we don't care about, how much water has left the tank. We just want to know, how much water has entered into the tank, not how much water is in the tank. So what can we do? All we need is what? Which functions do this here? Yeah, just f of t, right? We just want to know how much water has entered into the tank, and we just take the what of f of t. This integral, yeah. So the integral of f of t dt. Use your calculator, but of course you're going to use x instead of t. So math 9 on f of t. From 0 to 7. It says round to the nearest gallon, so 80 to 64. Part B, find the time interval in which the amount of water in the tank is decreasing. So we found that, right? So decreasing is what we highlighted in red. So from 0 to 1.6, and then from 3 to 5.0. And the reasoning is because our g of t is greater than f of t, right? G of t is the rate at which water is leaving. F of t is the rate at which water is entering. Okay, so between 0 and 1.617, and also between 3 and 5.076. Part C, at what time is the amount of water in the tank the greatest? So anytime we see least or greatest, max or min, we're involving extreme value theorem. So we're going to test endpoints. And critical points. But if we're asking for where the tank is greatest, do we need to test 1.6? This is going to be more of a relative min, right? This is going to be decreasing followed by increasing. We know that's not going to be a potential. I mean, it's not wrong if you test 1.6, but we don't need to test this. So that's a relative min. At 3, that's a relative max because we're going from increase to decrease. And then at 5.0, that's going from decrease to increase. So we don't have to test this one either. We only need to test 3, 0, and 7. 0 and 7 being our endpoints. And they all go into our A of t equations. So we have our amount A of t similar to that formula that we built before. That we're taking into account 3 things if we want to figure out how much water is in the tank. how much is there to begin with, how much has been added, and how much has been removed. So let's create that formula for part C. So we're going to test 0, 3, and 7. So A of 0 is just going to be 5,000. This says the initial amount water in the tank is 5,000 gallons. A of 3, we're going to include the 5,000 plus the amount added. So from 0 to 3 of F of T minus the amount removed. So between 0 and 3 hours, the rate is a constant 250. So minus integral from 0 to 3 of 250 T, right? We want to make sure that everything that we're plugging in is in terms of our rate, so that the rate can turn in terms of gallons, so that we have gallons plus gallons minus gallons. So in your calculator, I got 5126.5. We also need to find A of 7. Now, we could start at the very beginning and start here, but I think something easier that we can do with A of 7 is that we can just pick up where we left off. We already know that there's this amount in the tank at 3 hours. Let's just figure out what's happening after 3 hours. So I'm going to let 5126.591 being my A of 3, my starting point. And then from there, I can figure out, okay, how much has been added after between hours 3 and hour 7, and then how much has been removed. And it's good to split up between 0 and 3 and 3 and 7 because there's a different rate. And that rate, we don't have to deal with that 250 anymore. We can move on to that rate of 2000. So we're going to subtract out from hour 3 to hour 7 a different rate that is different rate of water being let out. So we have this amount of water 3 hours in, and then this is the amount of water that's been added between hour 3 and hour 7, and this is the amount of water that's been removed between hour 3 and hour 7. If we total that together, we're going to get how much water is in the tank 7 hours in. Okay, so use your calculator. So now we just compare these 3 values. We're looking for the absolute max. So between these 3 values, the most that the tank is going to have is at 5126.
For part C, when we're writing that interval, do we have to write it with the inequalities, or can we write it like with parentheses?
Oh, I see. I got you. Yeah. You don't have to use. You can use decreasing on interval from 0 to 1.617, and then use parentheses. Right? Yeah. You don't have to use that interval notation. It's up to you. And so I highlighted the radiant radar problems that I wanted to do with you, but your homework is going to be pages 1 through 6 from this packet. And we talked about on Friday how the homework for the AP review is going to account for 50% of your quiz grades after Thanksgiving. So if you do your homework on time, you're going to get that 50%, 100 points out of 50% of your quiz grades after Thanksgiving. So, but I'll send out a reminder, and I think there's a key attached, so you can just check your answer as you work through. Let's move into our quiz review for area volume. I want to just make sure I do a little bit of that each day. So let's look at page 7. Right, let R be the region in the first quadrant, bounded by y equals root x. So root x is the curve. Horizontal line, y equals 6, and the y-axis. Right? Find the area of R. So area, we could do top minus bottom or right minus left, but I think for us, if we ever see an area problem, our default should be top minus bottom. And if that doesn't work out, then I think we should try right minus left. But for this problem, I mean, you could do it either way, but top minus bottom is usually going to be easier. It says non-calculator, but you can just do the setup without the calculator and then plug in your calculator, which is fine. You'll get to use your calculator on your quiz. Okay, so the top of my rectangle is sitting on the y equals 6. The bottom is sitting at the y equals 2 root x. And I'm just doing top minus bottom. Careful that sometimes we feel like this is not enough. We feel like area needs more than this. Sometimes students start putting a square or start putting a pi, and that's only for volume, right? So your area should look simpler because it's only a 2-dimensional unit. It's just top minus bottom and the integral of that. Part B, write but do not evaluate an integral expression that gives the volume of the solid generated when region R is rotated about the line y equals 7. So we know that anytime that we're rotating around an axis, you're having to decide between this method or washer method. And also you got to decide, is it a top minus bottom or is it a right minus left? Right, so look at the dotted line, look at where this is located in relation to your shaded region. This will have to be what? Washer method. And the axis is horizontal, and we know the radius has to come out forming a T with the axis. So we know it's got to be a vertical radius. Radius always involves dotted lines, so you're going to extend two radius, one that will extend from dotted line all the way to the curve, and the other one from dotted line to y equals 6. And part B is only asking you to do the setup. Part C, any questions so far? Region R is now the base of a solid, so now we're doing volume by cross-section here. For each y, the cross-section of a solid taken perpendicular to the y-axis. So that's an important decision we have to make. Which orientation do we want to draw our base length? Horizontal, right? So pay attention to both words. If you just don't look at perpendicular, or if you just look at y-axis, you may assume one thing or the other. So make sure that you are carefully observing those two words and how they're related. So y-axis starts off vertical, perpendicular, we got to make it horizontal. So if we see a horizontal, we know that we have to make some adjustments with our equation. Our equation as they stand are not going to be in a good form for right minus left. So our equation initially was 2 root x equals y. That's the curve. But I'm going to solve for x. So I'm going to divide by 2 first. And square both sides. Or y squared over 4. So we know that this is going to refer to this curve here. We know the other graph is involving the y-axis, which is x equals 0, and they're both in the form that we want. In terms of x equals, we know whatever is on the right is good for our right minus left formula. So let's build our base length. Our base length is just simply y squared over 4 minus 0. And we can drop the 0 since it's not going to make any impact. And with cross-section, you're kind of building everything one dimension at a time. So our first dimension is just the base length. Our next dimension is area. And we got to figure out what shape we want to build. We want to build a rectangle. So rectangle is base times height. And they're describing height for us, right? They're describing height as being 3 times the length of the base. So what's the height going to be? Yeah, 3y squared over 4. So we have our base, which is y squared over 4. We have our height, which is 3 times y squared over 4. Merge that together, and we have our area. Once you have your area, then your last step is to involve the integral. The integral is going to give it that third dimension. And our bounds, we're stacking these rectangles from the lowest y value to the highest y value. They're basically coming out of the page. Lowest y value is 0. What's the highest y value? 6. You can include the square in your calculator, but I'm just going to distribute it because it's felt like it's easier to plug in without a set of parentheses. But again, I think in this problem, it's only asking for you to evaluate. This AP practice problem is non-calculator, so usually they don't have you do more complicated problems, but you can also plug this in the calculator and be able to get that volume. Page 9. Few minutes here, but we can get started with this. So it's just top minus bottom graph, and that's it. No square. We don't square this expression. We don't put pi in front. You can plug that in the calculator. I worked it out by hand, but you can use your calculator on the list. Okay, so tomorrow I'll have a help session for your Thursday quiz. And I'm going to go over basically pages 9 through 13. But that also, so your morning review is going to be that. I'm not going to have a help session for your quiz on Thursday. I'm doing a help session for AB. So if you feel like you need some additional support, come in tomorrow. But otherwise, I feel like you should seems like you feel pretty good about area volume. So hopefully you do feel that way. There is homework tonight, and homework is off of the FRQ topics review, pages 1 through 6. I'll send a reminder. The key is in the packet, but the new the FRQ unit is password protected, and I'm going to send that password to you so that you know. I'll send a reminder tomorrow about this afternoon about your homework due, as well as help session tomorrow. Okay. Okay. I'll mark you down. Thank you. Have a great day, guys. See you tomorrow.
So during at the end of this, after one, like last grateful.
Yeah. So in the packet that you just got, I have the update.
Okay.
So we're gonna have, after we get up from break, we're gonna have a table of values quiz. We're gonna have a FRQ quiz over some topics. And then there's gonna be Friday, it's gonna be a partner multiple choice quiz.
Okay.
That'll be the last. And they're all gonna be buffered by your homework.
Okay, thank you.
Really?
I'll finish. Okay. I'll mark you. Thank you.
See, we also have like a whole liver pack, like it's like an innovation project. So I think she might try to